Hello, everyone. Welcome back to freepilotgroundschool.ca. This is our advanced lessons for dumb pilots series, and we're going to talk about engine thermodynamics. So how heat is transferred within an engine, and this isn't. It's kind of maybe like halfway between a pilot and an engineer. So it wouldn't quite be the depth an engineer would go into it, but hopefully you'll learn something out of it. How a bit more about aviation engines, kind of beyond what you would have learned in your ground school. So let's get started with temperature or definitions. And actually, before we start with temperature, let's just talk about thermodynamics. So thermodynamics is kind of the movement of heat. How does heat move within a system? And so this comes up very often. I mean, we can talk about obviously engines, we can talk about air conditioners, we can talk about heat pumps, and we can even talk about the universe and how things are created, all sorts of things like that. So it's a very broad field, and we're just kind of going to skim the surface of it as it relates to aviation. So let's talk about first temperature. So temperature is the average kinetic energy of the particles in a substance. So perhaps you learned this in grade school. Everything's made up of particles, atoms, molecules, and they vibrate. And the higher or the more they vibrate, the higher the temperature is. Okay. So temperature is what we call a scalar quantity. It doesn't have a direction. It's just a magnitude, right? And we can kind of dumb it down. We say it indicates how hot or cold something is. We have different units. We have Kelvin, Celsius, Fahrenheit, and there's actually also another unit called Rankine, which is odd, but it's kind of like Rankine is what uh, what Rankine is to Fahrenheit, what Kelvin is to Celsius. Okay, so 0 degrees Celsius is 273.15 Kelvin, uh, and room temperature is assumed to be 293 Kelvin. Let's talk about pressure. So pressure is the force per unit area. Unlike temperature, it's a vector quantity, has a direction and a magnitude, right? So it's pushing down in a certain direction with a certain amount. And the unit, the standard international, the SI unit for pressure is the Pascal, PA, or often we talk about just PSI, pounds per square inch. Okay. So let's just talk about magnitudes a bit, just so you can get an idea of like what a Pascal is. So 1 Pascal is 1 Newton per meter squared. So a kilogram mass weighs 10 newtons on the Earth. Okay. So if we had, uh, let's say roughly 100 grams, and we spread that 100 grams out over a square meter, um, that would be a Pascal. So that would be like very, very low pressure. Like you're barely feeling that. So I think that would be like a Pascal. I bet you a fly landing on you would be less than a Pascal, or sorry, more than a Pascal. That's how little it is. So when we're talking about atmospheric pressure and things like that, we're talking about kilopascals. So atmospheric pressure is approximately 100 kilopascals. And then once we're starting dealing with like pressures in turbines and engines and things like that, we start getting into the megapascals. So millions of pascals, so millions of newtons per square meter. Let's talk about energy. Energy is the property that can be used to do work. Okay, the unit is joules. Okay, and we can have different types of energy. We can have kinetic energy, so something's moving. We can have potential energy, so that's an object that's at a height that can be converted to kinetic energy. We can have chemical energy, nuclear energy, everything like that. And then we can have internal energy. So sometimes internal energy is called thermal energy, and it's a type of kinetic energy. So normally when we think about kinetic energy in school, you have these roller coaster examples. Roller coasters going down, it goes this fast, it has this mass, therefore this is the kinetic energy. And so when we talk about internal energy, we're talking about the total kinetic energy of the particles inside of a substance. Okay. So it includes both the kinetic energy of the individual particles as well as the potential energy associated with the positions of those particles. So whether those particles are close together to other particles and then are repelled or vice versa. And again, internal energy is measured in joules. Okay, I'm not going to talk about internal energy anymore, but I thought I would bring this up. So let's talk about work. So work is the energy that's transferred to or from an object. And it's again, it's measured in joules, just like energy is. And it can be mechanical. So when we talk about force times distance, or it can be a fluid. Fluids can do work as well. And hopefully right about now, you're not like, okay, I've done it with here, there's an integral symbol. He wants us to do calculus. This is really silly. We're not doing this anymore. I give up. I'm quit. But let me explain it to you. And hopefully if I can explain it to you pretty clearly, you get something out of it. So we have this equation here, work equals P, so pressure, times V2 minus V1. So the volume 2, the end volume minus the first volume. So it's basically pressure times the change in volume. Okay. And then this is the integral symbol if you like your calculus um, on the right side. So it's the area under pressure with respect to volume. So you might be wondering, like, why do we have to do calculus? Well, if we look at the first part, the work equals pressure times V2 minus V1. That would pretty much be the average, right? But when we look at that pressure might be different at different volumes, right? And so if we want to be more precise, it's going to be that pressure might change as we apply a force. That in that case we'd end up using calculus, but it essentially means the same thing. And so if we look at this diagram, the change in this piston, we'll just call that ds, or actually if we apply it to the equation above, it would be dv. So we apply a force, and then of course we have the force, we have the area of this piston, and you have this working fluid. And so it ends up being the equivalent to uh, the work equaling force times distance, which is kind of the mechanical force that we were talking about. Let's talk about heat. So this gets a bit more complicated. Heat is the transfer of energy crossing a boundary of a system by virtue of a temperature difference across the boundary, right? So if we have something that's hot and something that's cold, okay, you're going to be heating something up. So you touch, let's say, a warm stove or something like that. That's kind of the hot reservoir, and then it heats you up. Okay, it heats something up. Okay, and that's what happens when we're talking about heat. And the unit is the joule, whereas the rate of heating would be the watt. Okay, so a watt is a joule per second. Let's talk about efficiency. So efficiency is work divided by the energy used. Okay, so when we say something is 100% efficient, it means that all the energy that went into the system was captured as work. Okay, and so something that's 50% efficient means that you are only getting half the work out of the energy that you put into it. Now here we get a bit more complicated. So we're going to talk about enthalpy, which is denoted by the H, the letter H is enthalpy. So enthalpy is the total heat content of a system, and it's given in joules per mole. So if you remember back from high school calculus, a mole is a given amount of matter. It's like, when we say a dozen is 12, okay, and a mole is 6.02 times 10 to the 23 particles. Could be atoms, could be molecules. So it's a lot of little molecules, okay, but it's measured per mole. Okay, so the enthalpy is the sum of the internal energy of the system, U, plus the product of pressure and volume, right? So when we add heat to a system, we can either increase the internal energy, or we could increase the pressure and volume, or both, I guess. Okay, and so enthalpy is often used to describe the heat content of a substance at a constant pressure. Next one, entropy. And this one's pretty pretty difficult to explain. And so I actually have to kind of somewhat dumb it down. So it's typically associated with a degree of disorder or randomness in a system. So typically when you went through high school physics, let's just say in grade 10 or 11 or whenever you took physics, that's how they described it because it's the easiest way to understand it is you just say, okay, well, something increased in entropy, so it has more disorder or randomness in the system. And so we'll stick with the simple definition, okay? But it does end up um, drawing on what's called statistical mechanics or probability, okay? So we can have ice, which is low entropy, and then it because it's in a crystalline form, and then it becomes water, it becomes uh, more disordered, okay? And so here, it's simple mathematical definition. So it's not a simple mathematical definition, um, but basically the entropy is going to be your heat divided by your temperature, or if we want to take a or a calculus definition, the change in entropy is going to be an integral um, or equal to the mass times the specific heat coefficient, CV, times the ln, your natural logarithm of your two temperatures, T2 divided by T1. Okay, but we're not going to get it that much in depth. But if you're like a geek like I am, and like you get off on these things, then yeah, that's why I put it in here. So let's talk about the laws of thermodynamics. So first off, we have the zeroth law of thermodynamics. So this one, I don't even know why they made this a law because it seems like pretty obvious to me. I don't know. Somebody probably won a Nobel Prize for this, but I don't know. It's like a 10-year-old could figure this out. So if two thermodynamic systems are in thermal equilibrium with one another and also separately in thermal equilibrium with a third system, then the three systems are in thermal equilibrium with each other. So you have like three blocks and they're all the same temperature, let's just say. So B and C are the same temperature. There's no heat transfer because they're the same temperature. And let's say A and B are going to be the same temperature, and so there's no heat transfer there. It means that A and C will also be the same temperature. So again, that's pretty obvious. And so here we have the first law of thermodynamics. Here we have Homer Simpson. It's like one of my favorite episodes from The Simpsons where Lisa makes a perpetual motion machine and Homer demands that in this house we demand the laws of thermodynamics, which is pretty funny. But when energy passes into or out of a system, the system's internal energy changes in accordance with the law of conservation of energy. So what this boils down to is that energy cannot be created or destroyed, but can only change forms. Okay, so it's pretty fundamental. This is why perpetual motion machines don't work. So if anyone ever is like, hey, I invented a perpetual motion machine, I think you should invest in my idea, uh, I would not invest in that idea. So the change for that is going to be Q minus W heat minus work. So you're it's pretty much always going to be less than unity. So or it will always be because you will always lose something there. Now we have a second law of thermodynamics. So the natural process tends to increase in entropy. So increases in disorder. And again, it's a bit of a dumbed down explanation. Then, you have your high school physics teachers like, yeah, notice how a room always goes from clean to being messy. And it's like, yeah, it does. But yeah, that's an example, but it's not really how things go. Um, but what is important is that no system gets more orderly without the addition of energy. You have to add energy to the system in some form in order to increase order, like to make something a crystal, let's say. Okay, and so this also explains why heat flow goes from hot to cold. Okay, here again we have um, these fancy mathematics explanation. How entropy is always uh, greater the heat divided by the temperature. And lastly, we have the third law of thermodynamics, and this has absolutely no application to aviation. It's more like a condensed matter physics thing, but I thought I'd throw it in there so you know that there is actually a third law which nobody ever learns about. So the system entropy approaches zero, S, approaches zero as the temperature approaches absolute zero. So entropy equals Boltzmann's constant kV times the ln omega. Again, you don't need to know it, but I threw it in there. So let's kind of get to more of the meat of the lesson now that we've got all those definitions out of the way, and we're probably about halfway through the lesson now, but just learning those definitions are important anyway. So we'll talk about a heat engine, and a heat engine is a kind of a theoretical construct that we use in thermodynamics to help explain or make explanations for these physical phenomena that we see. So it's a heat engine is an engine that uses heat to produce work. It extracts this heat from a reservoir, leaving the second reservoir colder. And so it extracts heat. So if you look on your right side here, right, you have your hot reservoir, right? And then you have your heat, goes down towards your cold reservoir at the bottom. So that is heating up the cold reservoir. But somewhere in there, we're extracting work, okay? Work is getting out. So there's a number of different heat engines in practice. So we have piston engines, which rely on what's called the Otto cycle. We'll talk about that. We have jet engines, which is the Brayton cycle. The refrigerators that are like the Carnot cycle. And then we have boilers. That's the Rankine cycle, the vapor cycle machine. And so we're just going to talk about the first two because they apply to aviation, the piston and jet engines. Okay. So let's begin with the internal combustion engine. So the internal combustion engine is used on almost all light general aviation aircraft in the majority of automobiles. I mean, majority of automobiles, I guess you have electric cars now, which is kind of cool. Like a few people made electric aircraft, but it's very, very rare. I don't even know if it'll ever take off, just the energy density of the batteries, but it's kind of cool. And then we're going to be talking right now, we're going to be talking about the gasoline engine. And the diesel engine is thermodynamically difficult. And thermodynamically different than the gasoline engine. So we're going to talk about the gasoline engine for now. And the reciprocating gasoline engine operates by the Otto cycle. So if you could recall from your PPL ground school, the internal combustion engine has 4 cycles, right? You have your intake, compression, power, exhaust. The intake of the fuel air mixture is sucked into the cylinder. Compression, it's compressed by the piston. Then you have your power, where it's ignited and burns, forcing the piston down. And then at the end, we have the exhaust stroke. And that's where the water vapor and carbon dioxide, so your exhaust gases, are forced out of the cylinder. So let's talk about how these different cycles apply in this kind of from a thermodynamic point of view. So here we have 2 graphs, okay? The first one is a pressure versus volume, and then the second one is temperature versus entropy, okay? So let's get started in the intake. And this is a gasoline engine, internal combustion engine. So a mass of air and fuel is drawn into the cylinder. So that's 0 to 1. Okay, so if you think what happens, the pressure basically stays the same in the engine. I mean, I guess technically it'd be sucking a little bit, but it's generally at equilibrium from 0 to 1, but the volume increases, right, as we're sucking this in. Okay, so that is our intake. So now we go to the compression. Okay, now the compression is from 1 to 2. Okay, that's what we're looking at. Okay, the fuel air is compressed in the cylinder. So you can see it's compressed, so the volume goes down, right? And the pressure goes up. Okay. This process is called adiabatic or isentropic. So if we look on the right side, 1 to 2, okay, the temperature is increased, but the entropy on the right side has stayed the same. Okay, so that's what it means by adiabatic or isentropic. So basically all we're doing is we're trading off some volume, so less volume, to get more pressure. Okay, so the entropy does not change. Next, we have our power. So it goes from 2 to 3. And so when we're actually looking here, this is not the point Contrary to popular belief, this is not the point where the piston is forced down. This is right when the fire starts, the burning starts, right? It's ignited in the cylinder, okay? So when this is at your top dead center, so your cylinder's all the way up, and the volume remains constant at first. It's right at the top. It just burns right for like a very, very short amount of time, okay? So you have this increase in pressure, right? The volume stays the same just for now. We'll get to the other part later, okay? But the pressure increases, okay? So this is from 2 to 3. If we look here, this is not isentropic, okay? We have an increase in temperature, right? The burning. But more importantly, we have a big increase in entropy. It becomes more disordered, turns into gas, something's burning, right? That means the entropy is increasing, okay? So the temperature and the entropy increases. There's an increased disorder in the system. And now this is the next part of the power stroke. So the power stroke is actually two things on this graph. So now we're going from 3 to 4. And this is the part of the power stroke where the piston is being forced down. Okay, so the combustion gases expand. Okay, so as they expand, we're reducing the pressure and we are reducing and increasing the volume, right? So this again is isentropic. Okay, so the fire is burnt. It's all done, but now it's forcing, it's expanding, and it's forcing, the gases are forcing it down, right? So uh, your temperature is now going down, but your entropy is staying constant. Okay. Okay. And now here again in the power stroke, this is going to be at the bottom of your power stroke from 4 to 1. Okay. So heat is rejected from the air at the bottom dead center. The pressure decreases while the volume remains constant. So this is at the bottom of your stroke, okay? So you see the temperature goes down and your entropy decreases. Now all of a sudden you're like, hey, what happened to our exhaust stroke? You know, like what's going on here, right? And so yeah, that's a really good point. So this exhaust stroke happens actually back from 1 going back to 0, okay? So the pressure remains roughly constant because you just opened a valve up and nothing's getting compressed. Volume goes down, okay? So that's what you would see on this side. And so this cycle assumes a closed system. It's just that this closed system happens again and again and again with each revolution. Okay. So the air fuel is allowed to enter into the system, which is what provides us the energy to do work. So that's the thermodynamics of an internal combustion engine. Let's talk about how much power this engine produces. So recall that power, so we talk about watts or horsepower, is the pressure times, force times distance divided by time. Okay, so can we derive our own formula? So we could have the force would be the pressure in the cylinder times the area, right? The distance is the stroke length. And then the time is the time for the piston to move down. Remember, you only get 1 power stroke for 2 revolutions. Okay. So you could have your power is your RPM times the area times your stroke length and times your mean effective pressure. Sorry, I said that backwards. So mean effective pressure, your area, so that's your cylinder area, times your stroke length, times your RPM. And then you divide it by 2 because we only have a power stroke every 2 minutes, and 60 because we have per 60 revolutions per minute, but we want to talk about in seconds. Okay, so that's our little derived formula. We can figure out how much the engine power produces. Let's talk about the gas turbine engine. Okay, so gas turbine engines, so in turboprops or jet engines, are used on almost all transport category aircraft. They also power natural gas power plants. That's how natural gas power plants work. And their big advantage is they have much higher power to rate ratio, much higher reliability than internal combustion engines. So if you're like an airline pilot, you've flown a jet engine, it quits like 1 in 100,000 hours. It's like 1 in 5 careers kind of thing. It's like so rare that it's ever going to happen. And then, of course, it's very light compared to the power that it produces, right? Its big downside is it's considerably less efficient than a piston engine, okay? And the gas turbine engine operates by a Brayton cycle. So let's talk about gas turbine engines. So the air enters the compressor where it is compressed. The compressed air is then ignited. The turbine blades extract energy from this air to power the compressor. And so in modern aircraft, a fan, you have a turbofan or a propeller, is attached to the shaft via a gearbox to create an engine with greater thrust and higher efficiency. So back in the day, years ago when they first had them, they just had turbojets. They didn't have a fan. It was just compressors, and they were awfully inefficient. So let's look at the Brayton cycle. So here we have a little diagram on here. So we have fresh air coming into the compressor, right? And then you have fuel is added. There's combustion, and then it expands in the turbine, and then you have the shaft and its work out. Then again here we have our pressure versus volume graph, right? PV diagram, and then our temperature versus entropy diagram, TS diagram on this side, right? And we're going to talk about this here in a little bit. So 1 to 2. So in the compressor, air is compressed adiabatically. So remember the entropy remains constant. So we're going from 1 to 2. Okay, so our volume is reduced, but our pressure is increased. Okay, we go from 1 to 2. Because it happens adiabatically, the temperature increases, right? And the entropy remains constant. Then we have from 2 to 3. So this is your combustion, right? So just think about what's going to happen with combustion, right? You have fuel added to the combustion chamber. And so during this combustion, the pressure is constant, but the volume increases. Okay. And so if we look at our TS diagram, the temperature obviously goes way up, right? But also because it's burning, your entropy increases. So this QN this is the fuel, right? During your combustion, this is your fuel going in. So work is going in, energy is going in, right? Okay. And then from 3 to 4, this is the combustion going towards your turbine. So 3 to 4. Okay. So again, it's adiabatically, 3 to 4. The temperature decreases while entropy remains constant. And then here in the PV diagram, you have a reduction in pressure, but an increase in velocity. So this is after combustion when things are expanding, right? And so work is produced by the turbine to drive the compressor or the gearbox, right? It's going from 3 to 4, going through the turbine. The hot gases expand, increase in volume, and decrease in temperature. And then they are allowed for further expand out the back. Okay. And they expand out the back and they convert pressure to velocity providing thrust. So that is engine thermodynamics for you. I hope you enjoyed this lesson, and thanks for joining me.